Good morning. Last few classes we have been talking about some of the application principles of physical metallurgy that we have learned. And we did talk about that most of the metals that we use, they are made up of several crystals, and these crystals in most cases are randomly oriented, but in certain cases it is quite possible that these crystals are oriented in a preferred manner. In that case, we get certain very specific properties or characteristics, and it is possible to exploit this characteristic in several applications, and we will see some of these. And under this topic, that preferred orientation, that application, what we will look at, if crystals are not randomly oriented, then it is likely that the properties will be not be same along all direction of the product. We will also look at how do you get this kind of preferred orientation. One way is the process of directional solidification. When you solidify or solidification process, the crystals grow preferentially along particular direction. For example, in cubic crystals, particularly bulk of the alloys that we use is face centered cubic, and many of these cases it is the cube direction along which the growth rate is maximum. So, therefore, it is quite easy to produce crystals having this kind of texture or this type of preferred orientation. We can also produce preferred orientation by cold working. We have seen that when you deform a material, the process of deformation is primarily through slip, and slip is a process of simple shear. So, there is some amount of rotation associated with it, and during the deformation crystals orientation change, and finally, the cold work material, when you recrystallize, you may get another type of preferred structure. We will look at whether alloy additions or the factors which that control this kind of preferred orientation that you get here. We will talk about few applications, one related to superalloy. We will also talk about some application where making sheet product, which are sheet products are made by deep drawing, how to get a good formability, so that they can be easily deep drawn and with minimum amount of rejection. And we will also talk about some applications in electrical steel, where when do we need preferred orientation and when we do not need preferred orientation, and how we can production route can be modified to achieve this objective. Now, if we look at the origin of anisotropy, so in general the crystals have some symmetry elements. In fact, the cubic crystal, they have maximum symmetry elements. Cubic crystal have some finite number of symmetry element. Even cubic crystal, which has maximum number of symmetry element, have different properties along different directions. So, this is I think we did talk about in detail, and we have seen, if we look at bulk of the cases, we look at mechanical properties, and which where elastic constant, and this is determined, mechanical properties are determined by elastic constants. And we have seen that in case of cubic crystal, you need 3 elastic constants, whereas for isotropic material it is good enough to have 2. And usually this elastic constant for isotropic material is, one is the Young's modulus, another we can take either one of the two. So, very often we use Poisson ratio as the other elastic constant, and if these two are known, the shear modulus can easily be found out. And in fact, for isotropic material, so we did introduce these concepts of stiffness and compliance, they are actually tensor. We looked at its nature, and what does this signifies? If we look at here, that C signifies it defines a relationship between stress and strain. So, if we say that if we want to find out stress along a particular direction, and then we say this is C I j epsilon j, where sigma 1, 2, 3, 4 say up to 6, these are, this defines the stress state, epsilon 1, 2, that is epsilon 1, epsilon 2 up to 6, that I or j, they vary from 1 to 6. This is the range, and repeated suffix means summation. So, you can imagine you have a large number of these constants, and there are certain symmetry rules which you can apply, like stress is a symmetric tensor. So, similarly strain also we can assume that this also is a symmetric tensor. So, you do not have, I mean you have certain limited number of elastic constant, and crystal having least symmetry element where we have 21 elastic constants. So, this is just a recapitulation of what has been done. Similarly, instead of, you can define strain also in the same way. This is S I j . Now, it is possible to show, if you look at this slide over here, it is possible to see, you look at how these constants are related in case of an isotropic material. In cubic, this relation will not be valid, the C44 will not be given by this these two. So, therefore, what we need in case of a cubic crystal, 3 elastic constants C44, C11, C12 or S44, S11, S12. However, if you look at this elastic constant of tungsten, this is an ideal isotropic material. Even a single crystal tungsten will satisfy this type of relationship. So, therefore, one point that you can infer, that polycrystals, which is made up of several or large number of crystals. So, in a fine grain you will have a very large number of crystals per unit volume. So, it is more likely that if finer the grain, it is more likely the property will be isotropic. However, orientation is rarely random, and what do we what will happen if the orientation is not random? Obvious thing is, say you may need, I mean the properties will be anisotropic. Now, let us see the origin of anisotropy. Why do we get anisotropy in a material? There are two kinds of anisotropy. One is a crystallographic anisotropy. Metals are made up of, have crystalline structure. Even in polycrystalline material, they may be, if crystals are oriented in a preferred manner, then polycrystalline material will also show that crystallographic type of anisotropy, and sometimes we call this crystallographic text arrangement as a texture. This has a certain preferred orientation or texture, and then it will have different properties in different direction. Another reason for anisotropic behavior of the material and a polycrystalline material is, many cases we have seen that the metals are not, I mean they are often not made up of single phase. There are certain amount of unintentional phases which are present, like inclusions, and sometimes some of these inclusions like manganese sulphide in steel, they change their shape, they get elongated during the plastic deformation or thermomechanical processing stage. So, in the material you will have this elongated manganese sulphide along the rolling directions. So, therefore, you have that arrangement, the macroscopic arrangement, microscopic arrangement, different phases, they have a certain pattern and which will make the property anisotropic. Now, let us see why does this type of anisotropy, crystallographic anisotropy develop in a material, and what are the factors which will determine. Obviously, deformation is determined by primarily by slip and twinning. These are the two modes of deformation, but bulk of the deformation in metals, they are through slip. Now, if you have a different crystal structure, it will affect the texture that you get. It will also determine by the process of deformation that you are giving. If this is being drawn, in that case you have one kind of effect. If it is being rolled, then you have another kind of effect. And if you recollect the drawing, so drawing is you have a die, and die like this, and your product, this is your sample, and you try to pull it through the die. So, you have reduction. So, this is your initial cross section. After drawing, this reduces to this. So, that means there is deformation in this directions, and in this directions there is a diameter reduces and the length increases. So, you can say that drawing is a process where you have two directions, you have reductions, and another direction you have elongation. And we also assume that volume does not change during deformation. So, this is one difference, whereas in case of a rolling, if you recollect, you have a slab passing through and you have a reduction in thickness. The thickness reduces. This is the initial thickness before rolling, and after rolling this is the thickness. So, there is a reduction in one direction and elongation in this direction, and the other direction perpendicular here, there is a negligible deformation. So, you can say this is a plane strain deformation, whereas in this particular case you can say this is you have strain in three directions. So, that is the basic difference and because the excuse me, state of excuse me, because the state of stresses are different, you get different types of texture, and which is listed over here in case of a drawing, and it changes depending on the crystal structure. In rolling you can get one type of preferred orientation, whereas in case of a drawing you get another. Now, this is a typical example which is shown, a metal which is made up of several crystals, and so these are, each grain means one crystal, and although in 2 dimension and figure that we see under microstructure, but these grains are actually a 3D object and it has a particular orientation, and we have tried to represent this orientation by this small cube, and you see in each of these cases the crystals are differently oriented. And this can be determined. There are different techniques, X-ray diffraction technique, electron beam, electron backscatter, diffraction pattern, that is this is a special attachment which is attached to scanning electron microscope. By this also you can explore the extent of the crystal orientation or textures which is present in the material, and you can also measure property along different directions, and you will find if the property is elastic modulus you can find in different directions, and you will find they are different. So, these are the evidence of crystallographic anisotropy, and this reason for this anisotropy is cold work. And if you anneal a cold work material, depending on the magnitude of cold work you get a typical annealing texture, and these are also altered by alloy addition, and also the microstructure also affects say different phases, if it is a two phase or the microstructure. If there are some alloy additions, then also they affect that texture that you get in the material during processing. And this is an example of mechanical anisotropy. So, here what we have what has been shown, that you have a inclusion something here. So, this is a material which has undergone large deformation. If you look up here, this is a manganese sulphide, they get elongated and maybe they will get elongated most of the time, and after during deformation, if it is hot working, these grains get recrystallized. These are the main grains, they get recrystallized. Let us say this is ferrite, this is manganese sulphide. So, these are non-metallic inclusions, they have a totally different characteristics. Bonding in this direction is not very good. So, if you measure its mechanical properties along this direction, you will find, since these are aligned, so you may find that better strength in these directions, but in this direction these boundaries they are weak and it fractures, and sometime. So, these are, and it also causes some problem during welding, it results in lamellar tearing. So, mechanical anisotropy origin lies in the microstructure, and particular one of these factor is the inclusion. And how do you control this mechanical anisotropy, or you want to avoid this anisotropy? You can control that amount, so have as little inclusion in the material as possible, and also you try to control its shape and size. By controlling shape and size, you can try and make the material as isotropic as possible. Now, since the materials have different properties along different direction, is texture hardening, is this a possibility? Now, bulk of the metal that you use, they are highly symmetric, they are BCC or FCC. Say aluminum is face centered cubic, steel it is primarily ferrite, it is body centered cubic. So, in this case, because of that high symmetry element, the scope is very limited, and if you recollect this relationship, that shear stress, this is the resolved shear stress, and because the deformation takes place through shear on particular slip plane. So, that means if you resolve the shear stress on the specific slip plane, it is the load that is applied, this is over cross section area. So, this is the tensile load that you apply to the test specimen, this is the shear stress on the specific slip plane, and this is the orientation factor. Cos phi cos lambda is the orientation factor. So, in a way you can say that ratio of tensile stress over shear stress, this is equal to this 1 over cos phi cos lambda. So, this is the orientation factor, we call this as m, that is the orientation factor. Now, what will be the minimum value of this? This is minimum when cos phi cos lambda is maximum, and we know that this is maximum when phi is equal to this equal to 45 degree. So, therefore, minimum m is this. Now, in case of face centered cubic, you have a limited scope for increasing or changing this m, and if it is perfectly random orientation, m is around 3.1, whereas in HCP metal there is a wider scope. So, if at all this texture hardening is to be exploited, you have to look for hexagonal closed pack structure and possibly ideal hexagonal closed pack structure. So, there only it is possible. Say if you want to have a dent resistant material, you develop a texture so that it is dent resistant. That will be possible only if the material has hexagonal closed pack structure. So, textures in metal nevertheless affect several other properties, and which are worth exploiting, and we will see how this is done. A quick look at the factors that control texture and the material. Obviously, the texture origin of that crystallographic structure we have seen lies in the cold work, the deformations. Now, in alloy, say particularly also alloy addition does affect the texture. Say if you cold work copper, you will get one kind of texture, brass you get another kind of texture. Origin in fact does lie in the slip, and the slip we know takes place through movement of dislocations. Now, if a material when you alloy, usually we find that stacking fault energy decreases. So, you have the perfect dislocations, they split up into partials, and stacking fault energy means low stacking fault energy means large distance between the partial dislocations. So, if the dislocations are split, they have little difficulty in slipping, in cross slipping. They cannot cross slip, they can move only in one plane. So, you can reason out one reason for why this alloy addition controls the texture is because the movement of dislocations they depend significantly on the stacking fault energy. Another reason for this texture that develop is a recrystallization process. Now, this when recrystallization takes place, recrystallization after recrystallization, the new grains that they form, they are not necessarily randomly oriented, they depend on several factors. One could be the amount of cold work that you have put in. So, already if it is a highly textured material, it is likely that recrystallized material also will have a texture. Again, if there are certain inclusion present, some carbon nitrides in steels, like if aluminum nitride, they actually develop a certain kind of preferred orientation. The inclusions or precipitates, if they are present in the material, they also will control the type of texture that will develop during recrystallization during process. Similarly, secondary recrystallization, this is the last stage of the recrystallization process, when few of the grains they start grow abnormally, and this happens when this precipitates, most of the time this precipitates when they dissolve, they are not able to pin the boundary, and if such a thing happens, you may have a different kind of a texture. In certain cases, this is exploited, particularly in electrical steels. Now, the question is what happens, how do you represent these preferred orientation, and we did talk about it. Pole figure is used to represent the preferred orientations. Now, here what we do actually in a represent it in a kind of a stereographic projection. Say suppose this is the base circle, say this is the rolling direction, this is the transfer directions, and if it is a perfect, let us say it is a single crystal you have, and we are trying to plot this 111 pole figure. This will be located, there will be 4 different 111 plane, and there will be, this will be represented by 4 pole. And in fact, if you have large number of such crystals in the material, it is very likely that if there are random orientation, they will be uniformly distributed all over this. So, if it is uniform, that means distribution, then it is a random orientation. But what happens when you cold work or something, they try to arrange along a particular direction. In that case, these are these intensity contours which are plotted, the density of poles, how many numbers of poles are there. So, instead of they are being located all around, they are located at certain isolated places, and this is called pole figure. And schematically I have tried to show this pole figure effect of cold work and rolling. So, this is if you have a 90% and 5% cold work, is a large amount of cold work, better is the texture that you develop. As what happens, it is not that I have just tried to show some of the places you will have 4 regions actually where these 1 poles will be located. So, if there is a pole here, these are diametrically. So, there also you may get some amount of reflections. So, they may be located in certain areas like this, or maybe it is not as perfect, maybe they are located as some of these regions, it is quite possible. So, this is the type of textures that you get in the pole figure, you get in a cold work copper. If it is brass, then you find that nature is little different. So, here the brass, so possibly it cannot cross slip because of that low stacking fault energy. You may find the type of texture that they develops is little different, and when you anneal, possibly in this case you get you are likely to get a particular type of, this is the texture, and if you say that this is a something similar to a cube texture, So, that means this rolling direction 100. If you anneal this cold work structure, get a different types. I have just schematic, you should look up that exact textbook to see how what a pole figure looks like. Now, let us see some of the applications. In certain cases, we know that to some extent anisotropy is desirable, whereas in certain other cases in undesirable. Now, look at the case of a sheet forming. How do you do sheet forming? You have a blank, and from that you are trying to deep draw and make a tumbler like this. This is a cylindrical object, and this is a sheet. A disc has been cut, and from this disc you want to give it this shape. So, the process is this blank is kept between a die and you push it through a punch, and there will be a particular this dimension, there may be some clearances are required, you may need a little lubrications, and when you push it, what happens, this flows and then the material flow like this. When this goes out, push it, this material flows like this, and finally, you get this type of a structure. And what is done, it is possible to find out the drawing ratio. This is the diameter of the blank is capital D, diameter of the punch is small d, and this ratio is called drawing ratio. And you can try to find out limiting drawing ratio LDR. So, how much you can draw? So, that means initially you see that this how large this ratio can be. If it is larger, that means it has a good deep drawability. Now, in that case, what do you need? So, you need high uniform elongations. There should not be any local deformation. We know in the stress strain diagram there is after a certain critical strain, local deformation takes place, there is necking. So, there should not be any necking to be avoided. So, the material must have high uniform elongation. There should be minimum strain in the thickness directions. Material should flow in this direction only. The deformation should be the planar deformation. Through thickness, there should be minimum strain in the thickness direction, and there should be equal strain along all planar directions. So, in different direction, planar direction, the strain should be as close as possible. If it is not close, in certain direction it flows more, or certain direction is flows less. Say suppose in this direction you get this kind of a structure, which is called earring. And another important thing is there should not be any yield point. Yield point also gives local deformation, Luder bands form, and which leaves unpleasant marks on the deep drawn product, and which customer will not like. So, therefore, question then comes, how do we satisfy this? So, in that case we need to have high plastic strain ratio, we said that what is this plastic strain ratio? Strain in the width direction, strain in the thickness direction, and this should be as low as possible and this should be high. And this is how you determine this. This is the width before deformation, this is the width after deformation. So, what you do, you have a sheet, and from this sheet what you do, you try and find out, you make specimens along different orientation. This is aligned along rolling direction, this is along transverse direction, this is at 45-degree angle to rolling directions, and this is also at 45, but in a differently oriented. This is oriented like this, this is oriented like this. And what you do? You do a tensile test. So, and W is the width and T is the thickness, and when you measure this strain, try to find out true strain, which is defined as log to the base e, natural logarithm of W naught over W. Similarly, this is strain along thickness directions, and often it is a little difficult to find out. You may find that often it is difficult to measure thickness. So, what you do in this particular case, what you do is you try to find out the length and the width, because thickness is it is normally very thin sheet. If it is a very thin sheet, it is accuracy is less in thickness measurement, and what you do, by volume constancy you can convert, you can know the calculate the thickness, and this is what has been done. I leave this to you. So, these are the initial dimension, this is the final dimension, and this is the expression for plastic strain ratio. And what you do when you do the tensile test on differently oriented samples, you get different values. So, this is the value R naught is the value of plastic strain ratio along rolling direction, this is R 90 is along transverse directions, and this is that 45 directions, and you have two samples. So, you find out average R bar, and what has been found out is this R bar value, this average R bar has a direct correlation with limiting drawing ratio. That means, this explains this it gives a better correlations or is a better indicator of the ability of the material to be deep drawn. So, R bar is a method, R bar is the property which which is a measure of deep drawability of the material, because most other deformation processes we go by percentage elongation, and you will find that even if you do, it is erratic. It does not have a direct correlation with LDR. And rimming steels, they have a relatively poor R bar, whereas in keel steel, because of aluminum presence of aluminum nitride, the material during deformation processing develops a preferred structures, and this has a high R bar value. So, R bar has better correlation with the drawability, and usually, and there are certain extra deep drawing grade steels where even this is goes close to 2. There is another problem we just mentioned, that is a problem of earring. If this deformation not uniform in all direction, so that means what you need here is the material should be anisotropic as far as the thickness direction strength is concerned, but the material should be isotropic as far as this planar deformation is concerned. So, if it is, that means it should not form that earring. If in certain direction, this is a earring problem. So, if you have to tumbler you are making, obviously you have to cut it out. So, that means there is a rejection, this is a waste. So, to cut down the waste, it is necessary the material should have should not suffer from this type of a earring problem, and this is possible when you find out R along different direction. You find out what is the maximum value of R and what is the minimum, and this range is called delta R. So, low delta R means this is the ideal. If this is 0, that is low delta R, this is the ideal material for deep drawing, there is no earring problem, whereas if delta R is high, then it is likely to have a earring problem. And R bar has a direct correlation with crystal structure, and which is given here. For face centered cubic, of course, you cannot get a very high because of that, whereas in BCC it has many more slip system, and here it is much, it has a better drawability. You can get even R bar as high as 1.8 in aluminum kill steel, or even certain extra deep drawing quality steel even higher. And usually here, if you have this kind of a texture, if the rolled surface is close to 100 plane, it has a lowest value, whereas if this is parallel to that 111 plane, then it has the highest highest R bar. Now, the problem of yield point is illustrated here, and we know that low carbon steels, which are actually the bulk of the steels are low carbon steel, and low carbon steel, the stress strain diagram, if you look at, there is an yield point phenomena. So, this is stress, this is strain, and this is the upper yield point when it exceeds this, and there is a serrated yielding here, and then it goes like this. So, you have uncontrolled deformation over here, and when this happens, there are Luder bands form on the surface. So, and these Luder bands, they leave uneven marks on these are highly deformed area. So, these marks are quite visible, and in fact, these stretcher marks, if you get on these, the product won't sell. So, one way of avoiding is, many of these steels, you give a temper rolling, maybe 2% cold drawn. So, after this you unload, and then then the stress strain diagram, it does not show, it is a smooth transition, it does not show yield point phenomena. But the problem is, they are also susceptible to strain aging. Left to room temperature long time, it can reappear, and if it reappears, then again because of the strain aging, again this will have a difficulty to withdraw. So, if temper rolling is done, you have to see that it must be deep drawn within a specified period of time, and if that time is exceeded, again that kind of temper rolling may be necessary. Another way of avoiding this altogether is not to have any interstitial in the material. Interstitial free steels do not suffer from this yield point problem, and also you may ensure that there is no yield point problem, you have some strong carbide former in the material. So, these are the ways by which you can avoid that yield point phenomena. Now, a quick look about last class we did talk about the creep resistant material, and bulk of these are polycrystalline. These are the materials which are used, and we have a potential as austenitic steel is also used as a creep resistant material. And as far as steels are concerned, this table gives you a comparison of the creep high temperature or creep resistance of alloys depending on their crystal structure. This is ferritic steel, this is austenitic steel. Of course, you need one criteria is you must have low creep rate. So, as far as this closed pack structure gives lower creep rate. So, here austenitic steel is preferred, but the other, you also want to have low modulus, low thermal coefficient expansion, and high thermal conductivity. In that case, the thermal stresses there will be minimum, because many of these high temperature materials, they often subjected to say repeated shutdown, then start up and shut down, and that is the time you have high thermal stresses. To avoid that, you need to have low modulus, low thermal coefficient of expansion, high conductivity. So, here ferritic steel scores over austenitic, but austenitic steel they have a lower creep rate, and also they have a better structural stability, because here if you heat it beyond a particular temperature, it again gets converted in austenite. So, that is one limitation of this, and there are attempts are on to improve this temperature range of stability of ferritic steel, because it has certain other attractive properties. And if you go to even higher temperature, then obviously you have to use even better material, and nickel based superalloy is another common high temperature creep resistant materials. Now, we did look at the process of the criteria for the selection of materials for creep resistance, and one of the mechanism of creep is movement of dislocation glide, but this glide is also controlled by climb process, because most of these particularly nickel based material, you have a high volume fraction of this precipitate, and these precipitates are quite large. So, if you have a dislocation, if you have this dislocation to move, it has to overcome this precipitate, and this can do by either by shearing or by avoiding this by through climb. And if you assume that this climbs over it, in that case we have seen last class, this is the expression, if you recollect, then we can make this process of climb difficult by making this larger. That means, if this is larger, it will need longer time to climb. So, this high T climb means lower creep rate. Similarly, you need to have large volume fraction of precipitate. In that case, you will also large volume and large volume fraction means the smaller distance, lambda is the interparticle distance, large volume fraction will be smaller interparticle spacing. So, you need to have shorter interparticle spacing and longer precipitate, larger precipitate. So, in fact, it is quite interesting. Let us look at the effect of texture on creep. And so, by this in fact, nickel based superalloys are very effective high temperature materials, and in fact, the initial superalloy they were polycrystalline. In polycrystalline, the failure takes place through cavitation, and these are the grain boundaries are the site where cavitation takes place, and particularly the grain boundary where the load is tensile. This is the tensile load. So, these are the grain boundaries where cavitation takes place, and because of that the effective strength decreases and they have poor creep property. Now, correspondingly, if you try to avoid these types of grain boundaries, say if you directionally solidify, then grain boundaries are aligned. In that case, you have minimum amount of grain boundary perpendicular to the direction of stress. In that case, found the directionally solidified alloy, you have fewer cavity sites, fewer sites where cavity can nucleate under tension. So, therefore, they are likely to give better creep resistance, and in extreme case you have a single crystal do not have any grain boundary, but again we need to have precipitate. So, what do you have is nickel based superalloy, you have gamma prime, and these gamma prime precipitates are coherent precipitate. Coherent precipitates have low surface energy, they are highly stable, they do not grow at growth rate is minimal, and so therefore, they have high structural stability and you have large volume fraction of precipitate, but the overall structure it is a single crystals, there is no high angle grain boundary. So, they exhibit very good creep resistance. In fact, cast single crystal superalloy blades, they have excellent creep resistance, and many aerogas turbine, even some new generation of power these land based turbines are also these are the potential materials to be exploited. But this directional solidification and quick look, this I have just named. So, this is a because they cannot be deformed. So, the material when you make the product, it should be near net shape product, and this is done by precision casting and lost wax process on investment casting. These are the technique, and this is the cube direction is the preferred direction of growth. This is the direction growth rate is maximum, and often this is also direction which has low modulus, and in fact, they have better thermal fatigue resistance, and many superalloy we also find this is the direction which has very high creep resistance. So, therefore, in nickel based superalloy this is the preferred direction that we want, and the reason for good creep resistance is absence of potential site for cavitation. And this diagram gives how the superalloy evolved over a span of just 50-60 years, and here only our understanding of the physical principle of the transformation and physical metallurgy was been primarily responsible in extending the temperature capability, which was around just around the World War time when this gas turbine was developed, and that is the time the initial blade material were made up of wrought alloy, and the temperature was around this. And today this turbine blade temperature can go as high as around 1000 degree centigrade, and it is the single crystal blade which can withstand this. So, in fact, this did not happen just in a increment. There has been incremental development. Wrought alloy also temperature capability by alloying addition, making creep difficult. It was possible to increase it substantially. Then came conventional casting, because if you increase the creep resistance too much, these material are difficult to deform. So, then other alternative is conventionally cast, the precision casting techniques, and then but these are still polycrystalline material. Then this directional solidification developed around 60s, and from mid 70s the single crystal blades became available, and they are currently is the most attractive material for aerogas turbine. And these are actually the alloy elements have a quick look which you can consider as a summary. You have certain alloy element which are present in solid solutions, and they are called solid solution or matrix strengthener, and these are the elements chromium, cobalt, moly, tungsten. Whereas, you also need to have precipitate. Some of these modern turbine blades, they have 70% gamma prime. These are the hard phase gamma prime former, and these gamma prime precipitates are primarily Ni3Al or Ni3Ti, or it can also niobium and tantalum also is a similar type of precipitates forms, and they are coherent precipitates. In case of polycrystalline material, you need to have grain boundary strengthener. Normally, in the grain boundary strengthener, they segregate in the grain boundary, and grain boundary, if alloy content is higher, they have higher strength. So, segregation actually is the key, the grain boundary strengthener. So, these are the grain boundary strengthener. You also have some carbide formers, and these carbides also will be present near the grain boundary, and they will also strengthen the grain boundary. And we also need good oxidation resistance. So, these are chromium and aluminum, they help develop a protective oxide scale on the thin oxide scale on the blade material, and this prolongs its life. And in fact, if you go for single crystal variety, then many of these need not be added, like grain boundary strengthener you do not need. But you need to increase its capability, you possibly need certain elements which have very high melting point. They are often added like rhenium to increase the solver's temperature or the melting temperature. So, in short, you can say the single crystal variety does not need grain boundary. So, they are actually linear alloys. And let us now look at another exploitation of this preferred orientation is in case of electrical applications. Now, electrical applications, see, one type of application is wherever like transformer, these are stationary parts. So, here you need a texture material, because iron, if it develops this kind of a texture, then this is the direction in which it magnetizes very easily, and this is a preferred texture. And in fact, if this is so, then this type of material will be have a exhibit a good soft magnetic property which is required in transformer. It should have, and in fact, this is a BH loop, which is, and the area of this BH loop is a measure of hysteresis, and this gives a amount of the heat that is generated during in a transformer. This can give an idea about the heat, and if you have a soft magnetic material with a minimum the hysteresis loss, that will be ideal, and this is possible by controlling the texture. If you try to develop this type of texture, this will be minimum. And also there is another way of improving cutting down that heat generation is the current that which is induced, that eddy current, and which is done by alloying. And usually this is the BH plot, that initial permeability is important, it must have high permeability, the slope is the permeability. So, this is 3.5% silicon, grain oriented. So, this is a textured material. So, here texture is preferable in transformer, because they are static, they are not rotating, whereas other extreme in rotors, it rotates. So, here the steel on which that winding is made, it should not have preferred orientation, is not desirable. So, you try to have non oriented sheet here. So, here you need an isotropic material, whereas here you need an anisotropic material. And so, these are the thing. In this particular case, obviously you will making a sacrifice, the mu is low, and if it is high carbon steel or cast iron, they are actually preferred as a high carbon steels, they are preferred as a permanent magnet. So, soft magnet, say like for transformer application, you need high mu, low hysteresis, and whereas rotor also you need high mu. So, you do add silicon and you have a better mu here, but point is you need random orientation, that non oriented sheet in this particular case, and magnetically soft alloy here, if it is have this kind of a texture, this is the parallel to the rolling direction, and this is obtained by controlling the processing. And in fact, if you look at the processing of that recrystallization of cold work structure, if you recollect for low carbon steel, you may some of the steel you may have a little low carbon steel. This is a typical annealing plot, and when you anneal, the hardness initially may increase a bit, but later on it decreases. This is a strain aging part, but let us forget this part here. And primary, when this recrystallization takes place, new strain free grains form, and after a certain stage, if this you go on increasing the temperature beyond a certain temperature, these precipitates whatever or inclusions whatever are there, if they dissolve, and that is the time there will be uncontrolled grain growth, and this is called secondary recrystallization. And during that time, what happens, this will be the initial grain size distribution, D is the grain diameter, and usually grain size distribution in an annealed structure, you have a log normal kind of a distribution. This is the frequency, you have that certain number of grains, this is say for this diameter, this is the frequency, so many grains have this diameter, so many grains have this diameter. And when the secondary recrystallization sets in, suddenly you find a bimodal kind of distribution, and towards the end what happens, this finally will disappear and you will have a large grain, this is the kind. And this secondary recrystallization texture, this is the Gauss structure texture, which is 110, and here this is the soft magnetic axis. So, therefore, by secondary recrystallization you can develop steel which is ideal for transformer applications. So, this is where it is preferred. So, therefore, what we looked at today, just to sum up, we looked at anisotropy. Anisotropy in certain cases it can be exploited, it is advantageous. We looked at texture hardening and we looked at its limited scope in cubic structures, but in certain hexagonal closed pack structures it is possibly it can be exploited. We looked at origin of anisotropy. We looked at certain other applications like where anisotropy is required. So, in case of a formability is an example where you need planar isotropy, but through thickness anisotropy. So, here you need a special texture to be developed in the material. We also looked at superalloy. This is the high temperature material. Textured material have better creep resistance. When you have this nickel based superalloy, if you have 110 direction as the direction tensile direction, then you have better creep resistance, and this is obtained by primarily obtained by controlling the solidification process through directional solidification. We also looked at electrical steel, and we looked at how this structure can be developed by controlling recrystallizations. By controlling the recrystallization is the key thing. Whether you have this precipitate or you do not have the precipitate, you get different kinds of texture, and this is the key to develop application steels for either electrical applications or formable variety of steel. So, with this we cover this chapter on application of preferred orientation or textured material, where and we just seen certain cases it is advantageous, and where it is advantageous, what is the method of developing the desired structure. With this we finish this topic, and next class we will take up a new topic. Thank you very much.